All right, let's head into the world of integrals. Today I'm going to be, uh, deriving all the trig integrals, excluding the inverse trig integrals, and we'll get to that. Of course, just like we did with derivatives, we proved all the trig derivatives, including inverse trig derivatives. We're going to do that eventually. I'm going to prove all the six just regular trigonometric functions in this video, because that itself is a lot, but I'm going to do the other six inverse trig integrals in another video. Probably not the next one, but another video. So let's start off with the integral of sine of x dx. So really the best way to prove this is just looking at, the integral. The integral is just reverse of the derivative. So and again, we have to look at our integrand here. Our integrand is really that result of our derivative. So which derivative gets us sine of x? And hopefully your answer is negative cosine of x. And then, of course, plus our constant of integration, because the antiderivative is, there's no d antiderivative. Well, this is actually the antiderivative, but we have to generalize it with plus c, because an antiderivative is part of a family of antiderivatives, right? So the reason why it's negative cosine of x is, again, because if we do the derivative with respect to x of negative cosine of x, right, well, we know that if we can take the negative 1 out of the derivative, and then ddx of cosine of x. And I proved derivative of cosine of x a while ago. I think it was the summertime of 2024. Look at that video. Use limit definition and angle sum formula for cosine. Look at that. So we know that this right here is just negative sine of x. So we have negative 1 times negative sine of x, which is just sine of x. And that right here is our integrand, right? And that's that result of the derivative, right? So this should make sense. Same thing with cosine, all right? Integral of cosine of x dx, right? So integrand is that result of the derivative, right? So which derivative yields cosine of x? Well, that would be sine of x, and then that plus our constant, right? The reason why is because, again, derivative with respect to x of sine of x is just cosine of x. And again, I proved a video. I proved a video. I had a video summer 2024 where I went over the proof for derivative of sine of x. Also, they use special trig limits, and I did do proofs on the special trig limits as well. So watch all these videos, please. All right. So these should be pretty straightforward. And now let's move on to the integral of tangent of x dx. So this one, again, not as straightforward as integral of sine, integral of cosine, because it's not that straightforward for us to, have that derivative that yields tangent of x. So what we can do is, using our quotient identity, where I'm going to use green here, where sine of x over cosine of x equals to tangent of x, right? This is true. I think I did a quick side proof for this in one of the angle sum videos or something like that. And it's just, again, opposite over hypotenuse over adjacent over hypotenuse multiplied by reciprocal. You should get opposite over adjacent, and that is definition of tangent. So that's why it works. Trigonometry days, guys. We're in calculus now. So what I'm going to actually do here is rewrite it as integral of sine of x over cosine of x dx. And now we're going to do a little bit of u substitution here. And so, again, the reason why u sub works is because the du part, the du, again, like if we think about derivative of sine, let me use a laser pointer here. Derivative of sine is cosine. Derivative of cosine is negative sine. So that's why u sub works. But in this case, if you set u as sine of x, that's not going to work as well. That's kind of pointless. I don't think that'll even work at all. So after experimenting, you'll see that if we set u equal to cosine of x, that actually works. So if we do u equals cosine of x, we'll have du equals to negative sine of x dx. So then we'll have dx equal du over negative sine of x. So now integral of sine of x over our u times du over negative sine of x. See that the signs cancel here, and we'll just get a negative integral of 1 over u du as our integral here, and then that'll just be negative natural log absolute value of u plus c, and our u is cosine of x, so then we'll have negative natural log absolute value of cosine of x plus c is our answer. We haven't officially talked about this yet in the channel, but why do we have absolute value for the natural log? Well, it comes down to, our argument with the 1 over u, right? Now, it's better if I talk about this in the context of something, like as general as like integral of 1 over x dx being natural log absolute value of x plus c, right? This is a true statement. It's not a true statement necessarily if it's just natural log of x. That is just not true at all. Now, the reason is because we don't know necessarily if this x in our integrand here is positive or negative. We don't know. So in order to account for a case where this x is less than 0, and again, because this ln of x here, its domain is for all x values greater than 0. So if we have an x value that is 0 or less than 0, well, is 0 would be undefined, but less than 0, we can actually deal with that case using absolute value. So that's why it's important to incorporate that, especially we're dealing with a family of antiderivatives, right? This represents the generalization for all antiderivatives. So we want to be able to deal with all cases. Okay, let's now integral of cotangent of x dx. Again, quotient identity. Remember, cotangent is the reciprocal of tangent. So just like tangent is sine of x over cosine of x, cotangent is just cosine of x over sine of x. Please don't make me prove this to you guys. This should be really straightforward. It's just if opposite over adjacent is the yielded answer, adjacent over opposite, which is the definition of cotangent, will be yielded. Okay, prove that if you want. The cosine of x over sine of x, adjacent over hypotenuse over opposite over hypotenuse. Do that if you want. But again, this is kind of expected that you know that. Again, it's super easy. I did it on the side in the angle sum video. I probably shouldn't have I didn't even have to do that, but I chose to. Just why not? It was a pretty easy thing to explain. So again, both cases here, we put our u's as the denominator, right? So in this case, I set the u as cosine of x. In this case, I'm going to set the u as sine of x. Hopefully, you're kind of getting the pattern here with u substitution, because it's really just understanding the du isolation or the dx isolation and how that's dividing. Hopefully, you can see that, of course, with respect to like reverse of the chain rule, and how it's literally the inverse operation. Hopefully you can kind of see it there. So if u is sine of x, du is cosine of x dx. Right, if u is sine of x, du is cosine of x dx. So then dx is du over cosine of x. So if we rewrite this here, we'll have cosine of x over u times du over cosine of x. The cosines will cancel, and then we have this simple integral of 1 over u du, and then that's just going to be natural log absolute value of u plus c, and our u is just sine of x, so natural log absolute value of sine of x plus c is our answer. Okay? Hopefully this makes sense. Our next next three? Yeah, next three are gonna be a little more complicated, or no, next two, right? One, 2, 3, 4. Next two will be a little complicated. We have secant of x and then cosecant of x. So integral of secant of x. This one, you have to be a little clever with it. I'm going to give you a second to pause the video. I don't often say this, but I probably should say it more. I want to give you a second to kind of pause the video here and see what kind of algebraic manipulation you can do here. Specifically, I'm going to give you a hint here because I don't want to be stuck for hours. But think about like how secant of x, its derivative is secant x tangent x. Like think about that. Okay, hopefully you gave it some thought. So we can do some algebraic manipulation here by rewriting this as secant of x times secant of x plus tangent of x over secant of x plus tangent of x. This is a true statement because these would cancel and we'd get the secant of x in our, only the secant of x in our integrand, but we just multiply the numerator and denominator by secant of x plus tangent of x. Okay, you're probably like, why did I do that? You're about to see. So now we're just going to do some distribution here with the secant of x. So we'll get integral of secant squared of x plus secant of x tangent of x over secant of x plus tangent of x. Now we're gonna, again, the denominator, right? Hopefully you notice the pattern. We're gonna set u to the secant of x plus tangent of x in the denominator. So then du will just be, okay, derivative of secant of x is secant of x tangent of x. Again, we went over all these derivatives. Just FYI, look at the past videos in this series if you're new here. I went over all these derivatives. So please watch those videos because I went over everything for the derivatives. So secant of x, tangent of x, plus then derivative of tangent of x is secant squared of x. So now let's rewrite it. So this is just secant squared of x plus secant of x tangent of x over secant of x, and again this should be dx, sorry. And then this should, let me rewrite this all. This should be u, and then this should be dx. Hopefully I did dx. Yeah, I did dx for these other ones. So then times, then I'm gonna, okay, fine, I'll rewrite dx equals du over that secant of x tangent of x plus secant squared of x. So then that's gonna be du over secant square. I'm gonna rewrite it this commutative property. So secant squared of x plus secant x tangent of x right here, and hopefully realize that these will in fact cancel, which is awesome. So now we'll get this simple integral 1 over u du. That should be natural log absolute value of u plus c. Just want to check, did I do my plus c's here? Yeah. So natural log absolute value of u plus c. So then we'll get natural log absolute value, and our u is secant of x plus tangent of x. Yeah, pretty unique way of doing it, but it's all about thinking about, it's all about finding that kind of pattern and finding that flow. And as you integrate more and more, you will get that flow. It should just come in your head. Now, again, just kind of a side note, side conversation here. Integration obviously is a lot harder than differentiating. You could practically take the derivative of anything if you really wanted to. If you learn, like, all your derivative rules, or in fact even just like log differentiation could get you there. You could practically do any derivative in the world. But with integrals, that is, integrating is much more challenging. Finding ways and techniques to integrate, it can be very challenging sometimes. And I'm being completely honest here. Like, that's why MIT has an integration B and not a derivative B. That's why Berkeley has an integration tournament and not a, well, they have an integration. I think, well, it's Berkeley math tournament, but I'm pretty sure they have like specifically an integration competition. Yeah, they do. So that's why they don't have a derivative competition as well. Integrals are much harder, okay? And that's a good thing. That's why I love integration. It's so unique, the different types of methods. It's not just like product rule, quotient rule, power rule stuff. It's much more than that. Like, you'll see stuff like King's rule and so many ways, right? Feynman's method. Like, such a unique field of math, in my opinion. If you can integrate anything, that's like terrific. But yeah, it takes a lot longer to master this compared to derivatives, and that's okay. So now for a final one, integral of cosecant of x dx. And going to give you a hint. It follows similar logic to this one. Think about the derivative of cosecant of x to help you out with this. Yeah, pause the video. Okay, hopefully give it some thought. So, using similar logic, cosecant of x, we can rewrite it as cosecant of x times cosecant of x plus cotangent of x over cosecant of x plus cotangent of x. So, as you notice here, derivative of cosecant of x is negative cosecant of x, cotangent of x. If you use the negative sign, I think it would work out. I'm not 100% sure. Actually, I'd have to look into that. But it will work if you do it this way, just doing cosecant of x plus cotangent of x. You just have to find the pattern, and that's what I'm trying to get at. So if we actually do the u sub here, well, let's first distribute the cosecant of x here. So then we'll get integral of cosecant squared of x plus cosecant of x cotangent of x, right? Cosecant squared of x plus cosecant of x cotangent of x over cosecant of x plus cotangent of x, and then dx. So again, using same logic, we're going to set our u to the denominator, so cosecant of x plus cotangent of x. We do our du. Okay, so again, derivative of cosecant of x is negative cosecant of x cotangent of x. And then derivative of cotangent is negative cosecant squared of x. And then this is dx. And then if we isolate our dx here, we get du over negative cosecant of x cotangent of x minus cosecant squared of x, right? That should be correct. Negative cosecant of x cotangent of x minus cosecant squared of x. Just to save time, I'm going to rewrite it and factor out a negative sign here. Negative of cosecant x cotangent of x plus cosecant squared of x, right? And if you distribute, negative sign should be exactly the same, right? Going back to your days of like rational, simplifying rational expressions, you probably have remembered, or, factoring out negative sign here. Should be something technique you definitely should know by now into calculus. So if we do that, I'm going to move here to the side a bit. So if we do that, then we'll get cosecant squared of x. I'm going to actually rewrite it as just cosecant x cotangent x plus cosecant squared of x, right? Cosecant x cotangent of x plus cosecant squared of x over cosecant x plus cotangent x, or no, this should be u, set that as u, times du over negative of cosecant of x cotangent of x plus cosecant squared of x. So now we can cancel these out. Right, beautiful. Y'all love to do it. So now we'll have negative integral of 1 over u du. Then we'll have negative natural log absolute value of u plus c. And our u is cosecant of x plus cotangent of x. So negative natural log absolute value of cosecant of x plus cotangent of x plus c. And those are our 6 general trig function antiderivatives. Great. Sorry for the side conversation there. I just kind of want to emphasize here that it's so fun integrating, and it's really nice to see the various approaches that people use to integrate. It's much more abstract compared to derivatives, and it's so important to learn, especially as a problem solver. So, yeah. See you guys in the next one.